Alright, so here's our second video on exponential and logarithmic equations, and you can probably guess since we focused in the previous video on exponential equations that we're going to focus on logarithmic equations, which is correct here. Now, the general strategy here is use properties to write a single logarithm in your problem. Then convert log base a of x equals y to a to the y equals x and solve for x. Now you might say it's already solved for x, but the problems we're going to look at are going to be a little bit more involved than that. Always, that's not even close. I don't know what I was thinking. Actually, I know what I was thinking. I was getting ahead of myself. Always keep domain in mind. I was starting to write domain down as I was writing the word always. Alright, so this here is actually very important. Now, we didn't have to worry about that with the exponentials, and the reason we didn't have to worry about that with exponentials is any real number can be substituted in for exponentials. But with logarithms, we do have to be careful of the values that we can plug in. So let's start with a relatively simple example here. Let's just go ahead and do 4 log of x minus 6 equals 11. Now, before I even go on and do anything else, I'm going to write domain down, because remember that logarithms have to have numbers greater than 0 plugged into them. So if x was 1, 1 minus 6 is negative 5, that's not okay. I can't put 1 in there. I have to put in something bigger than 6, actually. So because x minus 6 has to be bigger than 0, which this just gives me that x has to be bigger than 0. So I'm just keeping that in mind so that when I solve my equation, if I get something that's not bigger than 0, I know that that is not a valid solution. Okay, so there's really not any properties here to use. You might say, oh, well, wait, you can use the exponent property and move the 4 up there, but there's not really a need to do that. What I would do instead is divide both sides by 4. So you'd have log of x minus 6 is equal to, well, 11 divided by 4, which is, I'll go ahead, since I can write that as a exact decimal, or a terminating decimal number is maybe a better way of saying it. This would be 2.75. And now we're going to go ahead and change this whole using this a y equals x. So what we're going to have then is that, well, you have to think about what's the base here. The base on the common log is, even though we don't write it here, it's 10. So since that base is 10, we would convert this to x minus 6 is equal to 10 to the 2.75 power. And then we add x to both sides, or not x, add 6 to both sides, and we get 10 to the 2.75 plus 6. And this would be, again, an exact answer. But if we want an approximate answer, decimal answer, we can of course just do this. and you get that this is approximately 568.3413, which is clearly much bigger than 6. But we might encounter in some of these later problems that we look at where that doesn't always happen for us. All right. So let's look at another example here. That's not too bad, but we're going to take two approaches to this and show how sometimes one approach might be simpler than the other. I think both approaches here are going to be about equivalent as far as difficulty, but some people might like one approach versus the other. So we have the natural log of the square root of x minus 8 equals 5. Now this is already a single logarithm, so the first way I'm going to do is just go ahead and reconvert this. Now what's the base of the natural log? Base of the natural log, of course, is the natural exponent, which is e. So we rewrite this as the square root of x minus 8 equals e. And I should have maybe said here that we know that x minus 8 has to be greater than 0, which means that x has got to be greater than 8. Even though you got the square root going on there, with the logarithm, the fact that we have to have things being bigger than 0 for the square root also gets us x being greater than 8. Alright, so back to the problem here. So we have now converted it, and it would be e to the 5th power. So square root of x minus 8 equals e to the 5th power. Alright, well now though we need to square both sides to get rid of that square root. So if we square both sides, so I have square root of x minus 8 squared is equal to e to the 5th squared. Well, the left-hand side is simply just x minus 8, and then e to the 5th squared, well again we multiply these exponents, so this would be e to the 10th power, and then the exact answer for this would be e to the 10th plus 8. And you're going to often want to leave these as exact answers. And the reason being is if you actually evaluate what e to the 10th is plus 8, oops, my screen came down here. You get x is approximately 22,034.4658. And so, yeah, it's a pretty big number there. So it's often going to be more helpful to leave it as an exact answer. And again, you have to follow directions anyway, so if it says to leave it as an exact answer, you'd have to leave it like this anyway. Alright, but let's look at the other way I said that you could approach this. And we'll get the exact same answer. Some people find this way more confusing, some people find it easier. It's really personal preference. So I'm going to go ahead and start using some log properties first. So I'm going to have that this is the natural log. Rewrite this as x minus 8 to the 1/2 power is equal to 5. But then that would be 1/2 natural log of x minus 8 is equal to 5. Multiply both sides by 2. And you get natural log of x minus 8 is equal to 10. Now I'll convert, and I'd have x minus 8 is equal to e to the 10th power. Add 8 to both sides, and you get x is equal to e to the 10th plus 8. And of course we get the same answer in both cases, which isn't something that should be too surprising. In the first case, we just applied some properties of logarithms first. In the first case, we just directly translated it into an exponential to get rid of the logarithm. And in the second case, we used some properties first so that we didn't have to do squaring of both sides. All right, so let's look at another example here. Let's look at the natural log of x minus the natural log of x plus 1 is equal to, well, apparently it didn't switch to black, whatever, equals to 2. Alright, now, same thing here. We want to first notice that x, the first logarithm says that x has to be greater than 0. The second logarithm says that x plus 1 has to be greater than 0, which would be x has to be greater than negative 1. Now these both have to be satisfied, so it's not an or here, it's an and. They have to both be satisfied. So that just means if you were to draw this on the number line, you could see it as well. That just means we have to be x greater than 0 here for our answers. Alright, so how are we going to do this here? Well, we're going to go ahead and apply some log properties here. So what I'm going to first do is, as I said, write this as a single logarithm. So this would be the natural log of x divided by x plus 1 is equal to 2. Now I'm going to go ahead and convert this using my exponential. And so this would be x over x plus 1 is equal to e squared. Now I need to go ahead and solve this for x. So, well, saying, well, I would multiply both sides by x plus 1 to get rid of the fraction. Now, when we've done this before, we say, oh, okay, we got to be careful though that x is negative 1, which is still true because you can't multiply by 0, but this, what I've circled already over here, I know that x isn't going to be negative 1 because x has to be greater than 0. Okay, so then we would have, of course, the x plus 1's canceling, and you'd have x is equal to e squared times x plus 1. Now you have to solve this, and this is somewhat symbolic because we have e here. I mean, e is a number, but it's somewhat related to solving equations symbolically. And what we mean by that is I'm going to still solve for x. I'd distribute this, so I'd have e squared times x plus e squared, but then I'm wanting to get all my x's on the one side, so I'd have x minus e squared x equals, and I somehow wrote e to the x there, should be e squared, equals e squared. And then we factor out an x, and so you'd have 1 minus e squared is equal to e squared. Now we can divide both sides by 1 minus e squared, so x is equal to e squared over 1 minus e squared. Now, before we just leave it at this here, we should verify that this is a valid answer, because this would be my exact answer, but remember, what do I know? X has to be greater than 0. So we should, quite frankly, just evaluate what this is approximately, just so I know whether or not this is a solution. So I'm going to do e squared divided by 1 minus e squared. And you get that this is equal to negative 1.1565. But wait, right up here it says that x has to be bigger than 0. And that's again because my original problem had just natural log of x. Well, then I can't have this working as a solution. Now if we look at this condensed version, the negative number would be fine. But this is the original equation here. So that's what's different here is the original equation. This is what we're dealing with here. We weren't dealing with this. We're dealing with this as the original equation. And so what we wind up with is that this is, since x has to be greater than 1 or greater than 0, we wind up with no solution. So this is why you have to always put down your domain here, because this again, this is the original problem we were looking at. Okay. All right, let's look at one more, kind of similar along those lines, so that we can kind of get accustomed to it. Now, this one I think is going to be a tiny bit easier, but let's go ahead and evaluate this here. So what do we got? We have the log base 2 of x plus the log base 2 of x plus 2 is equal to the log base 2 of x plus 6. So I've got logarithms everywhere here. Well, I'm not going to actually have to combine them all onto one here, but I do have to combine the ones on the left-hand side. Basically, if you can have logarithms on both sides of the equation, and that's fine, but you can only have a single logarithm on each side of the equation. So using property here, this would be log base 2 of x times x plus 2 is equal to the log base 2 of x plus 6. Now, one thing I didn't do here, so I should do off to the side here, is what does x have to be? Well, we get x has to be greater than 0, x has to be greater than -2, and then also x has to be greater than -6 from those three logarithms there. So this is the one that we have to still focus on, because that's the most restrictive of the domains of each of these individual logarithms. All right. Now I'll go ahead and just multiply these out here. So this is log 2 of x squared plus 2x is equal to log base 2 of x plus 6. Now, some people want to subtract and then divide, but I think that's not really needed here, because remember one of those inverse properties, we put it in the previous video, we could write this as 2 to the log base 2 of x squared plus 2x is equal to 2 to the log base 2 of x plus 6. Basically, I'm doing these as exponents, I'm doing 2 to those, and since we have inverse properties, this is going to just boil down to having x squared plus 2x is equal to x plus 6. And now I just have a quadratic equation to solve. So I'd write this as x squared, subtract x from both sides, so we'd have plus x minus 6 equals 0. Now we factor. This does factor to x plus 3 times x minus 2 equals 0. And then, of course, we get x equals -3 and 2. And then I see people leaving it like this, and then they get actually a significant amount of points taken off on the problem. And you might say, why would you get a significant amount of points taken off? Because you're missing the whole point of finding these domains. X has to be greater than 0 in order to be a solution of the original equation. And so what that means, of course, is that -3 is not a solution, because that's clearly not greater than 0, and we have x equals 2 is the solution. So there's only one. Now, it's possible this equation could have had two solutions. It's just, with this particular example, we had it such that the one of the solutions was negative. But if you had two positive solutions, you would have been fine. Alright, so this is marking the end of our videos talking about solving exponentials and logarithmic equations. The next thing we're going to do to wrap up our discussion on exponential and logarithmic equations, or functions, is we're going to do just a couple example problems, some story problems of applications dealing with them. Okay?